design for multi-material fabrication. Yeah, there we go. And Kiril will present.
Hello. So my name is Kiril Vidimce, and I will be presenting the work on Foundry, a system that we've built that enables hierarchical material design for multi-material fabrication. And this is joint work with Alex Kaspar, Wang, and Wojciech Matusik. So there are several reasons why we pursued this work. First of all, even though multi-material fabrication is currently still in its infancy, and existing multi-material platforms are typically only used for rapid prototyping, we fully expect that in the near future, there will be multi-material fabrication platforms that will truly enable mass production of objects made with spatially varying materials. The question is, what kind of tools will we need to build to fully leverage these platforms? Further, our motivation for this work also stems from recognizing the fact that materials encountered in nature and also in the world of engineered materials are typically multi-scale. Our desire was to create a tool and a workflow that makes it very efficient to fully exploit these multi-material fabrication platforms of the future. Oops, whoa. Let's see. Okay. So let's consider two example materials found in nature. One's found in plant leaves and human bones. Leaves are composed of multiple layers, and each layer has a complex hierarchy of cellular and microcellular structures that form the various tissues of the leaf. Similarly, bones have a highly hierarchical structure that delineates it into a spongy and a compact bone. The spongy bone is then made out of a network of osteons and ancillary structures and vessels. And then finally, the osteon is made of concentric shells of cells that surround a central canal, completing the hierarchy. Engineered objects have a similarly hierarchical design. Consider this combined tire and a wheel, also called a tweel. In the first level of the hierarchy, the tweel is split between the thread, the carcass, the suspension layer, the spokes and the hub, and with multiple separating barriers. Then each component has further hierarchical details, such as this foam suspension layer, which is made out of cells, foam cells, with varying cylinders with different radii. Our key contributions in this work are a graph formulation of material design, where the materials are described by hierarchically instantiating and wiring parameterized operators that describe discrete actions over regions of the object. Second, a library of over 100 operators, each of them classified in one of three major groups. And finally, an interactive real-time preview system that enables a more fluent and rapid design of the desired material composition. Foundry can also be thought of as a volumetric modeling tool. And of course, there is a rich body of literature that describes other approaches to solid modeling, including Cutler's procedural language for solid modeling, first described in 2001, the work on data-driven modeling, such as using lapped solid textures by Takayama et al., and modeling with diffusion surfaces also by Takayama and collaborators. Wang et al. In 2011 described a multi-scale vector volume approach that uses a binary tree of sign distance functions to describe complex internal structures. Foundry, in contrast, has a more general decomposition model and focuses specifically on fabricating physical structures and objects. Finally, OpenFab, described in 2013, described a software architecture and a programming model, including a domain-specific language specifically for multi-material fabrication. This is a predecessor of Foundry, but unlike OpenFab that requires programming skills, and the actual material compositions are described using these programs called phablets, Foundry presents a high-level abstraction and a high-level workflow that enables non-sort of technical, non-coding kind of users to efficiently design complex multi-material compositions. There are also several commercial tools that have recently been developed that tackle fabrication specifically. So one is Symvol, which is a plugin for Rhino that focuses on procedural modeling of microstructures. NetFab includes a module called 3X for lattice construction. And finally, Monolith, which is probably the closest in spirit to Foundry, is a powerful voxel-based modeler that uses existing geometric models and textures as constraints for its volumetric operations. The workflow is, however, slightly more geared towards creating solid geometry, whereas the focus in Foundry is entirely on spatially varying material compositions. Let's dive deeper in Foundry. In its essence, Foundry allows the user to either explicitly or implicitly via the user operations in the UI to build a graph of operators that describe various operations over the volume. A trivial graph may simply assign a single material to the entire volume, such as in this case, we're assigning a simple white material to the bunny. A slightly less trivial graph may use a subdivision operator, such as a planar split operator, to split the volume into two subvolumes and then assign two different material compositions to each subvolume. In general, through our own experience of designing multi-material objects, we've discovered certain design patterns. Each new operator that we ended up designing and writing ended up being classified as one of these three types of operators. A subdivision operator that subdivides a volume into subvolumes, a remapping operator that transforms a given subvolume and serves sort of like an adapter role where it can adapt the coordinate space of one subvolume for use by another operator. And finally, a construct and assign material composition type of operator that typically creates the final structure of the spatially varying materials in the given subvolume. These operators are nested in a graph, and the relationship between the three of them is such that sometimes they can actually be recursive. They can be recursively nested. So let's look at some example subdivide operators. The simplest subdivide operators accomplish a simple binary inside-outside split of the volume using parametric geometry. So for instance, the geometry can be as simple as a cube, a cylinder, a sphere, or a plane. But our library of operator has a rich set of other more complex geometric primitives, including parametric surfaces and even generalized meshes. Next, subdivision of spaces can be achieved using various lattice structures. So the lattice subdivides the volume into individual lattice cells, and even the cell itself can be split between edges of the lattice, the vertices of the lattice, and then the actual fill space within the cell. Finally, distance-based subdivision can be a powerful mechanism to peel off the volume in various application-specific ways. A classic sign distance function can serve as a boundary distance subdivision that can be used to create onion-like shells of the object, each shell being assigned a different subgraph of operators. The distance itself can also be parametric. In this case, we used a thresholded Perlin noise to carve out an interesting structure on the surface of the bunny. One distance-based subdivision operator that we found extremely useful and typically hasn't been described in other systems. So this operator is very useful for traditional mechanical CADed parts. And this is what we call the surface distance operator. So unlike the traditional sign distance function, or that I named the boundary operator, this one works it's tied to a specific surface that's part of the solid part of the volume. So, for example, how is this useful? Consider the ski that we designed in Foundry. The top sheet of the ski is made out of a retroreflective surface. And the retroreflective surface was created by carving out these tiny corner retroreflectors. So on the left, you'll see a zoom in of a photo of the printed object, and on the right is a preview in Foundry. A specialized retroreflector operator carves out the negative spaces by using distance queries from the surface. However, if we were to use a traditional science distance function, these retroreflective operators will end up sort of wrapping around the ski, even on the edges of the ski, which is not something we want. We want to tie the retroreflective feature specifically to the top of the ski. So it's very useful to essentially say, I just want to make distance queries from this top surface, which is part of the assembly of the catted part. Finally, we also provide a number of different other distance operators, such as a point distance operator, which can be used to do spherical decomposition, a line distance operator, which can be used to create skeletons for like characters and muscles in them, and a mesh distance query operator, which allows distance queries from an arbitrary coupled mesh surface. A second class of operators are the remapping operators. In addition to classical linear transforms, such as translate, scale, and rotate, we provide operators that map between rectilinear, cylindrical, and spherical spaces. These are especially useful when adapting existing operators that were written to operate, say, on a rectilinear space. So a rectilinear lattice can be adopted to work on a radially symmetrical space, such as a cylindrical object, for example. Finally, to construct and assign material composition operators create spatially varying materials and patterns that can be either parametric or data-driven. Sometimes it's convenient to combine these three classifications into a single operator. For example, this fiber sandwich composite operator can be seen as a meta operator that actually includes all three of these characteristics into one operator. So, for example, this operator subdivides the space into in a planar fashion to create the sandwich of layers. Then every other layer gets remapped and rotated. And then we lay out fibers using a rectilinear lattice. Even the fibers themselves can be seen as cylinders that basically carve out the space inside versus outside. Our library has over 100 operators, and more technical users can always use a built-in operator editor to either edit the existing operators or to create new ones. Ideally, these operators will be published and shared in an online community. New operators can also be built non-programmatically simply by collapsing existing subgraphs and selectively publishing the input and output parameters of such a metanode. So in this example, we are creating a very simple graph. It's basically a stratification that stratifies this model into an inside and an outside material. And then we can select a subgraph of that graph, select the parameters that we want to make public, and essentially instantiate a new metanode that will replace the subgraph. And that metanode is automatically added to the library. A list of the most commonly used operators is described in the supplementary material, so please peruse that if you want to see the other kinds of operators that we've built in our system. A key component of our system is real-time preview capability. So Foundry provides a variety of interactive slice and voxel preview models, also a general mechanism for restricting the region of interest, which can significantly speed up the preview, especially when done at target printer resolution. We also provide a number of volumetric introspection tools, such as the wedge tool shown in the bottom middle of this slide. The wedge tool essentially allows interactive non-planar slicing of the volume to allow for internal introspection of the material composition. So here are three different preview modes, for example, combined into one viewport. So in the top right of the viewport, there is a slice preview. In the actual viewport itself, there is a 3D preview of the voxels. And then a wedge tool was activated to expose the internal guts of the Tweel. Let me briefly describe the execution architecture of Foundry, which enables us to achieve real-time preview capabilities. So I will first describe how we compile the operator graph, then discuss the partial evaluation and caching employed by Foundry, and finally describe the real-time execution model. First, the operator graph gets compiled by a meta compiler that generates the final phablet written in the OpenFab domain-specific language. A just-in-time compiler takes the input operator parameters, which are treated essentially as constants. It does the necessary binding of parameters, constant folding, and other compiler optimizations to bake in and produce the final optimized runtime function. Simultaneously, the internal fabrication system in Foundry will partially tessellate, voxelize, and also construct all the acceleration structures, for example, for distance queries, for the given region of interest. These together with the compiled phablet are then made part of the execution engine and its cached state that gets then reused every time the user modifies one of the parameters of the operator. During execution, we form a hierarchy of voxels similar to image pyramids. We progressively refine while continuously displaying intermediate results until we reach the target printer resolution, at which point we perform a material dither and display the final results. So we have used Foundry to build several interesting real-world examples. First, we built this Tweel that is inspired by a real-world non-pneumatic tire wheel. It has a complex structure, and it employs many standard library operators to subdivide the space radially, to create lattice structures, for example, for the spokes, to remap the space from a cylindrical to rectilinear so that standard lattices and foam can be used throughout the Tweel. And the only custom operator that we wrote was to create a parametric thread generator that creates the ribs and the sipes and the cable fibers in the thread of the tire. Here's the resulting graph of the Tweel. As you can see, it's a non-trivial graph, but it's still fairly compact. So essentially, it's a very compact representation of a relatively complex structure and a material composition, given the fact that the starting geometry was just a torus. To demonstrate that this is a real part, we mounted a Tweel on a toddler tricycle, and I even recruited my son to road test it. Next, we generated a functional ping-pong paddle. The initial geometry was rather simple, but we created a 3D marble pattern on the handle and the blade. There's a sponge layer above the blade, and then the two different sides. One side we have a sweet spot on the smooth side, and then all these pimples, the grooves on the other side. The input geometry was an assembly of 5 simple 3D boundary representations, so hence the resulting graph has 5 roots. And if we zoom in on one of them, for example, the one on the handle, you can see how it works. There is a cube operator that carves out a lot of the empty space inside the handle. This is an attempt to make the handle a lot lighter because the materials that we used were pretty heavy. And then there is a stratum operator that splits the outer shell and the inner shell. So the outer shell has this marble pattern that's created using cellular noise, and then the inner shell has fibers that provide reinforcement beams in the handle to make it stronger. We created a toddler ski with a complex internal structure that has a spatially varying mixture of an elastomer to make the ski bendable, but also rigid beams to reduce torsion. The top sheet has a retroreflective surface and various decorative patterns, and then the bottom has anti-skid grooves. And here's the resulting graph that describes the material composition of the ski. The internal material composition actually was data-driven. So we ran a stress-strain simulation to identify maximum stress points when bearing weight from a simulated toddler. So we wrote a custom operator that loads this data and dynamically distributes the different materials to achieve both flexibility and desired strength. We designed a helmet with complex decorative and safety features. And finally, we designed a bone with a complex hierarchical structure that reproduces some of the key features of the spongy bone, such as the marrow cavity, the osteons, and the intercellular structures. I'll conclude with a few remarks of what I think would make sense to tackle next. Foundry takes an approach of what I call direct material design, whereas other systems, including the one that was presented in this session at the very beginning, have a more functional design where users typically specify certain constraints, and then the system comes up with the material composition automatically. I think both approaches have their merits, and the ideal system, in my opinion, would include both of these components and also a very fast simulator that can be used to predict behavior. I think that the challenge here is how do you integrate these three things together in a seamless system where one can use this constraint-based modeling, but also be able to basically dive in and do a much more direct design of material composition. And of course, how do you build a simulator that can do multi-material simulation at 10 micron resolution? That's a big challenge too. I would like to thank a number of folks that helped make this system, the results, and the final paper and video. And I can take questions as I run a simple demo session that builds the Tweel. Thank you.
All right, we have a little bit of time for questions. Well, let me ask one quick question. This seems extremely general. What can you talk a little bit about limitations? Maybe not. I would ask, like, what can't you do with this, or maybe what is hard in your experience with it?
I mean, I would say it is fairly general. So I think maybe what's hard is that it would be hierarchical structures where you need some kind of a state, to form the structure. So, for example, L systems. An L system would be challenging to describe in this context. And we've looked actually at ways of integrating this into this pipeline. So there is a way to do it, but right now, Foundry doesn't support something like that.
Manohar, Microsoft Research. So the gap between this complex design and manufacture and production, we could design extremely complex objects, but how do you bridge the gap between making that a real object with the material properties that you intend to have? Which are the complex parts in producing 1,000 Tweels at,
Right. So that's basically what I referred at the beginning, that essentially right now we don't have these fabrication platforms because essentially 3D Systems and Stratasys are the only companies that currently sell commercial multi-material printers, and the materials that they use are not really durable enough to be used really for functional parts. And of course the materials are extremely expensive, so they can't be really competitive with traditional manufacturing methods. However, there are plenty of signs that point that this will change in the near future. I'm pretty sure that very soon we will see multi-material fabrication platforms that we will be able to use for final manufacturing. And in that case, it will make sense to have a tool like this. Because right now, certainly, if I had a Stratasys Connects that allows me to print with many materials, it would be almost pointless to use this tool to design a part, because then at the end, when I want to go make 1 million of them, how do I do this? There is no traditional manufacturing method to replicate this process, essentially, of spatially varying many materials. But it will come. I think in the next several years, it will be here.
Okay, let's stop there, and let's give this speaker and all the speakers a hand.
Thank you.
And I think all